Okay, so for the folks who don't know me, I'm Gilad from Mellanox. I'm going to share this session, as Scott says, with Arlene, talking about collective offloads. I thought I'm going to be the second, but I'll be the first. I'll try to be short. So I don't think that I need to explain to you what MPI is. If you have any questions, Steve Wood probably is a great guy to ask questions about MPI. And I don't need to explain to you what MPI collectives are. Few notes about why collectives are important and why they are in the focus. And I think they were discussed in a previous presentation, and we have full half an hour for this presentation. Is that collective operations typically have the most critical influence on performance, since they gather all the processes in a given system. And definitely you want to run them as fast as you can. You want to minimize any local delays of single processes because they're going to influence the entire application performance. And typically they consume a lot of a high percentage of the CPU cycles, right? If you're looking on blocking collectives, for example, when you start doing a collective operation, the CPU in that process will start doing polling on the memory. So beside of cooking an omelet on that CPU for that point of time, there is nothing that's going to be done. So offloading MPI collectives to the network, there are two main reasons for that. One of them is overlapping, and it's all the work that is being done right now in MPI 3. If you participate in MPI 4, I think there is few people that are. Then overlapping is one of the things. And the second one is minimizing jitter. And of course, if you have lightweighted OS, that's always help. But that was the goal of offloading MPI collectives to the network. A few comments. So first, offloading, when we talk about offloading, is that means moving them. Some people talk about offloading collectives by moving them from one piece of code to another piece of code, but still they are under the CPU control. When I refer to offloading, that means move them away from the CPU to something else in the system that will take care of them. And offloading collectives to the network is not because InfiniBand verbs it's too complex to deal with, or InfiniBand verbs it's not efficient enough, and so forth, or that InfiniBand verbs was designed for 100 nodes and now we're dealing with 10,000 of nodes, and not because vendors need to try to look in higher performance and they must go to collective offloads. The main reason for collective offloads is because of overlapping. That was the major reason for the project that was started as a DOE-funded project. It's overlapping. It's moving the collectives outside of the CPU, and for eliminating jitter or minimizing the jitter effect on performance. So quick example. If I take, for example, one nice algorithm that is being used for collective, which is recursive doubling. Basically what that algorithm does is that it's going to make sure that all the processes going to exchange data between themselves. There is a laser somewhere? Not this one. It works. So there is multiple stages in this simple example. The first stage, you see process 1 going to send data to process number 2. And then process number 2 is going to send data to process number 1. Right? So at the end of that stage, process number 1 is going to have the data from himself, of course, and also from process number 2. The second phase, 1 going to send data to process number 3, and 3 is going to send data to process number 1. So at the end of that stage, 1 will have the data from himself, from process number 2, and from process number 3, which also include data from process number 4. Then the last stage, 1 will send data to 5 and receive from 5. What 5 is going to send to 1, it's the data from 5, the data from 7, the data from 8, and the data from 6. So at the end of that iteration, basically 1 is going to have the data from everyone else. Same all other processes. So one issue is what happens if there is a small delay in process number 1, and that could be because the CPU went to do something else at that point. First, process number 1 is going to be delayed for the entire algorithm, but since process number 1 sent data to process number 3, 3 is going to be delayed 3 sent to 7 and 1 sent to 5, so those are going to be delayed. And if you have more than 8 processes, the entire system is going to be delayed. So that's one issue. And it's basically, if we move out the management of the collective operation from the CPU to something else, you're going to minimize that effect, which is the jitter effect. Another thing is typically when one sends the data to 2, it's going to start doing polling on the memory to see when it's going to get the data from process number 2, and in that period of time, besides of polling on the memory, it doesn't do anything else. So this is the overlapping item. So put everything on a table. The reason to move away the collectives from the CPU to the network. First, you can gain higher performance because if the network does it, then you save the time for the data to go from the network to the memory and back. So if you do it right, you can save some time and run the collective faster. But if you're looking on CPUs today, 2.9, 3 gigahertz, multiple cores, it's running pretty fast. The main reason is the negative effect of a single node on the entire system, which is the jitter. So moving that to the network, you minimize that effect. And the second one is reducing the overhead and doing overlapping. So if you're running the collectives from the CPU, as efficient as you can be, still CPU does it. And if you want to get to maximum overlapping, which goes well with MPI 3, then you want to move it to something else. So for example, on a software stack, what is being provided for doing those collective offloads? First, if you have InfiniBand HCA that has the offload, that's a good match. But then there is a new API within the driver, within the open driver, which is called Core Direct API, which is basically API that enables you to utilize the hardware resources that exist for offloading collectives or for managing collectives. On top of that interface, you can do multiple things. First, you can take an MPI and modify MPI to take advantage of that interface, of that hardware offloading interface. It's going to be more work on the MPI side. It could be more complex. From the other side, you're going to have full control, and you can do things more efficient to your design or your applications. There are also vendors who provide, for example, FCA. That's something that comes from Mellanox, which basically does all the collective offloads in that piece of code, and then the integration to the MPI is very simple. All right, that interface to MPI does interface barrier, roll reduce, and so forth. And the integration to the MPI is very simple, and then all the complexity of modifying the collective to take advantage of the hardware is there. And the collective offloads API was also designed to be able to offload sequence of other operations. So any other application that has multiple sequence of operations that are being done one after the other by the CPU and are related to messaging, those libraries can also take advantage of the hardware offloads. And it's also available for other applications rather than just MPI. That's my last slide. How do I do on the time? Good. Good? Yeah. Time for coffee? Okay. I want to show you one results that Oak Ridge published. So Oak Ridge National Lab, working on the interface of the offloading, modifying a version of OpenMPI to take advantage of it. Part of the work was to look into the advantage of overlapping, which was one of the main reasons to do collectives in the hardware. What you see here is a very simple application that basically does compute, which is resembled by BusyLoop, and then barrier. So the time that you see on the y-axis is basically the time per iteration. An iteration is a compute or a busy cycle period and then a barrier. And was comparing what happened when you run MPI as is from the software versus what happened when you take the MPI and you take advantage of the offloading that exists for overlapping. What you see on the x-axis is the busy loop percentage, which means how much of the CPU I can dedicate it to the compute side versus not to the compute side. So first you see there is advantage of running the collectives in the hardware just because it's run faster. But the bigger reason for me showing you that graph is is what happens when you want to increase the CPU availability. So increasing CPU availability results in immediate increase in runtime. Because if you increase the time of the CPU, you also need to have time in the CPU to dedicate it for sending and receiving data, or for the networking work, or managing the collective. If you take advantage of the hardware to manage the collective operation, you can increase the CPU availability. This was nearly 90% of CPU availability while maintaining a flat line of latency for that iteration. And that's the main reasons for doing offloading, which is basically doing the overlapping. I think MPI 3, the portion of non-blocking collectives is pretty much done. I think it was voted, if I remember correctly, and I think we'll start seeing some MPI that support it in coming months, more or less. So that was my section. If you have any questions before I move to Arlene.